So we're gonna start with a review of where we left off and what we took up the last week. So we want to build a system of equations so that ax is equal to b from a system of linear equations which will be given something like this. I heard it was confusing some people, so we've moved away from that notation of just using x. And I'm going to call the variables y and z for now. And we have these two equations, 1 and 2. Now the way to solve this problem is, first of all, we order our equations and we stack our vector of unknowns, which in this case is x. So the first thing, I get x is equal to, I'm going to put y and z. Mind you, we can have either of these things, but I'm choosing it to be this way. The next thing that we want to do is order our equations, like fix the order. For the first case, I'm just going to assume 1 is 1 and 2 is 2 and stack them together in the vector b. One thing to note is our constants are already on one side, so it shouldn't be a problem. I just get my vector b directly 5 and 6. Now what's left to do is, these are the only things you had liberty with, and now you can't change anything, and you have to find out the coefficients for the system of equations. So I get a is, so the coefficient of y in the first equation, because we're going to do it in order this time. So the coefficient of y in the first equation is 1. The coefficient of z in the first equation is 2. Then the coefficient of y in the second equation. Now, note the order. The first equation, we got the coefficients of y and z from the first equation, and b is 5 here. Similarly, for the second row, we want to look at the second equation, so b is 6. You get the coefficient of y, which is 2, and the coefficient of z, which is 3. And that is your A matrix. Now to find the uniqueness of the solution, we need the determinant of A to not be 0. So in our case, the determinant is 3 minus 4 equals minus 1, which is not 0. So we have indeed a unique solution. Now, another way of setting up our problem is, I'm going to use the same set of x, but I'm going to switch out the equations. So my equations are in reverse order. That is y plus, so my first equation is 2y plus 3z is 6, and my second equation is y plus 2z is 5. This is the first one, and this becomes the second one. From here I get b is 6 and 5, not 5 and 6. And as you would guess, the A matrix would now change according to our new setup. We will get the coefficient of y from the first equation, which in this case would then be 2, and the coefficient of z from the first equation, which is 3. The same from the second equation, you get 1 and 2. These two are not the same. You will see that their orders are reversed. But when you do the determinant of A, it is still 0. It's not the same, but it is still 0. So you still get the same conclusion that your solution is indeed unique. Now there's 2 more permutations to this thing, and I'm going to go over them just so we're clear. These permutations will come from changing my x. So I'm going to do, let's just mark this thing properly. So this is case 1. This is case 2. Now I'm doing case 3. And I know that now my x is reversed. So z first and y after. So z first and y after. And I want to get my equations are in the same order, so original set of equations. And I want this in green actually. Sorry. So the original set of equations that we had before. From there, we get B is 5 and 6. 5 and 6 like we had before. Then you want to get the coefficient of y and z from the first equation, which we know it is 1 and 2. But because our x is reversed, actually let me write it down. So our equations are y plus 2z is 5 is the first, and 2y plus 3z is 6 is the second. From here, when I'm building A, I want to look at the coefficient of z first this time, so it'll be 2, then the coefficient of y, because my x is such that z is the first variable and y is the second variable I'm looking for. And similarly for the next part, it's 3 and 2. Now the determinant of A is 4 minus 3, not 0, and we get the same thing. Now for the final case, this is the extent of the permutations and combinations you're going to get from this thing. I get x, z, y. My set of equations are the new ones, which is 2y plus 3z is 6 as my first equation, and y plus 2z is 5 is my second equation. I get b is 6 and 5. From there, I get A is, look at the first coefficient of z in what is now my first equation, which is 3, and I look at the coefficient of y in what is now my first equation, and that becomes 2. Similarly, it's 2 and 1. The determinant of A should still not be 0. It's 3 minus 4 equals minus 1, not 0. So we did it a couple of ways, and we found that they're equivalent and they solve the same system of equations. It's really just ordering either your x or your pair of equations which changes the order of b. And it feels like it's a new problem, but it really isn't. It's just reordering the same problem. Before we move on though, I want to take up one more problem of review in the same scope. So I'm going to set up a problem that is, I'm going to give you equations in the y is equal to mx plus z form. So let's say y is 3x plus 2, and let's say another set of equations is, let me use c here so people don't get confused. It really doesn't matter though. It's 3, what do I want to say? I'm sorry. Yeah. So let it be z plus y plus 3 is 0. Now before we did all of this, I cheated and I gave you the system of equations where everything is, all the variables are on the left hand side and all your constants are on the right hand side. That's not always the case, and before you end up building your b and your x matrix directly from this form, you need to rearrange it to get our equations in this form. So what you would want to do before you do all of these analyses is that you'd want to rearrange terms on both sides and I want so let's just do it here actually. So your equation 1 can be written as y minus 3z is 2, and equation 2 should be written as y plus z is minus 3. What was important was that for my sake, for convenience, what I did was I ordered my variables in a way that the left hand side is more organized and is in order like y first and then z. That just makes it easier to look at the A matrix. If you're able to do it otherwise, well and good, but just for people that are struggling, order it in a way that it's convenient for you. Put all your constants on the right hand side, get all the variables on the left hand side, and order them. And your life will be so much more easier, because now what I have to do to build my, first of all, to build my X matrix is I'm just going to use the variables in order. I'm just going to do y and z. I'm going to keep the same order of equations, and I'm going to put b, directly read it from the right hand side because I arranged it in a way that I can do that. So I can do 2 and minus 3, and then finally for a, I literally just have to look at these coefficients in order and fill them up, and it becomes 1 minus 3, 1, 1. Piece of cake. And then the determinant of a is 1, this term, minus of minus 3 times 1, which is equal to 4, is not 0, and we have a unique solution. Okay, Now you could do all the 4 things on this one as well. You're gonna get the same answer, which is that the solution is unique. And if you're having trouble building AX is equal to B, I encourage you to do that for yourself. If you have problems, do reach out in office hours, because this is essential for you to understand. We really need you to be able to do this before we go into solving actually and finding out different approximate solutions for how to solve AX equals B. Okay, so I'm gonna move on from the determinant part. We're gonna post the notes here and hopefully they're descriptive enough for you. Now, a solution of a system of linear equations. So, when we're doing AX equals B, we've learned how to build a system of linear equations into this form. And now what's left to do is we want to find a solution for our vector of unknowns, which is usually represented as x in this equation. And there are some tricks to solve this for us. We can sit down and do it by hand, but as we've realized, when there's more variables in the equation, it just becomes really cumbersome to do it by hand. And we want to look for solutions where there's a pattern. So for a special case where A is a triangular matrix, we can solve the system of equations using two techniques called forward and backward substitution that really makes our lives easier. Before we go on, from our lectures, we know what a triangular matrix looks like. It's basically a triangle. Basically, a matrix looks like a triangle, either in the upper part or in the lower. If it is if it forms like a right-hand triangle in the upper part of your matrix, pictorially, if we were to draw it, it's something like this triangle. You know that your matrix is indeed upper triangular. And similarly, if I was to do it for the lower part, it becomes something like this. Now, another thing to note here that people might have a problem with is when you're writing your A matrix. A very common way of writing your notation. So what I'm going to do is I'm going to write A00, shouldn't start with C, that's why people that do C have a problem with stuff like this. So A11, A12, A13, A21, so on to A and N. So when we say that a matrix is upper triangular, we say that it follows a condition or a rule which is given by this little rule right here, which is Aij is 0 if I is less than j. What that means is I is all of your rows and j is all of your columns. So when I say, let's say A32, then I is 3. I don't know what happened there. Give me a second. Yeah, sorry about that. Yep. So, sure. Yeah. So when I say A32, I mean I is 3 and j is 2, which will be this term right here. And if we were to find that term in our upper triangular matrix, it is, so third row 1, 2, 3, and the second column 1, 2. So this, my bad, this 0 right here. So that's A32. I feel like I did something wrong. Yeah, my notation is flawed, like if you'll see in the appendix. I'll fix it before I give it to you guys. But the idea is that if I is greater than j, my bad, then it is upper triangular, and the opposite in this one. I got it right in this one, I just forgot to put it there. Anyhow, so this is not less than, this one's greater than. I'll fix it in the answer sheet. Anyhow, so if I is greater than j, then that term should be 0. Similarly for A33, which is A31, which is third row, first column, I is 3, j is 1, I is indeed greater than j, and I note that aij is 0. And that will be true for all of our terms below the triangle, below the diagonal for an upper triangular matrix. I want you to observe a similar thing in the lower triangular matrix. I'm not going to go over it, but it's very easy to see. Actually, let's do one of these here. 8, 2, 3. I get I is 2 and j is 3. The condition for this one is indeed j is greater than I, in which case I note that aij, which is second row, third column, so this thing is indeed 0. And so we know what we have is indeed correct. And from our lectures, we know the fact that for solving upper triangular matrices, we use the method of backward substitution. And in here we use forward substitution, something you will see why, but hopefully if you followed along in the lectures, you already know. Now, let's get more practice on this, but this time I'm not going to use the simple y and z. We're going to use more complicated variables. We're just going to use x1 and x2. So, just to keep consistent, I'm going to write my x as x1 and x2. Then I write my b, it's 24 and 14. And from these two, because I haven't changed the order of my equations or of my variables, I'm just going to look at the coefficients directly. And they become 2, 2, 0, 2. Now, from our discussion of triangular matrices, we can see that this is indeed a, oh, why didn't it do it? Get it. This is indeed a upper triangular matrix. We also know from our facts that a determinant of a matrix that is triangular is given by the product of all the elements on its diagonal. Now, for a 2 cross 2, however, we know how to calculate a determinant, so I'm just going to do it so that we can see why, if it's actually true. So the determinant for this A matrix is 2 times 2 minus 2 times 0, which is 4. Now, if you were to do it using fact 1, there's only one fact here. I know that my determinant is equal to the product of the diagonals. So just, sorry, drop my mic. Okay, the determinant of A for you is then going to be A11 times A22, which is this term multiplied by this term right here, which is 2 times 2 is 4, and those two are equivalent, and you can see why. Because if it's an upper triangular matrix, all these terms right here will all be 0 below the diagonal, and then you end up multiplying any of the terms that are not on the diagonal, it comes out to be 0. So essentially they're equivalent. It's not just something, it's an easy fact to remember, and I think, but this just helps you build an intuition of why that is the case. So if this was 0, so if this is 0, which is always true in an upper triangular matrix, this 2 right here could be anything. We don't care. It would still be an upper triangular matrix. So we say we're gonna note that our determinant is indeed not 0. So we indeed have a unique solution, and A is upper triangular. Moving on, that was the simple case of 2 by 2. We could do it simply because it was a simple case. We're gonna move on to equation with 3 variables. I'm going to build my x vector again. It is x1, x2, x3, keeping it in order. Then I'm going to keep my equations in order and build my b vector, which is this. I use all of this information to fill out my A matrix, find out the coefficients of x1, x2, x3 from the first equation. So x1 is 2, x2 is 3, and x3 is 4. Then, in that same order, find out the coefficients from the second equation. The point to note here is that there is no x3 in second equation, so the coefficient of x3 is 0, coefficient of x1 is 6, and the coefficient of x2 is 7. And this is what we called in lecture the problem of missing coefficients. Which was also true for the case above though. But I'm going to point it out in this one. Now for the last equation, I do the same thing. I put the coefficient of x1 as 9, the coefficient of x2 is 0, it's not in the equation. The coefficient of x3 is 0 again, it's not in the equation. Now, I do know how to solve the determinant of a 3 by 3, but you really don't need to know it. I only know it because my undergrad course was not as great as this one. From our fact, we're just going to trust that the determinant of A is given by the product of the terms on its diagonal, which is A11 into A22 into A33, which for this case comes out to be actually, this is the, it's harder to teach when there's nobody here. So this isn't actually an upper triangular matrix, but you'll see it very closely resembles it. There is a triangle, it's just that we don't know what to call this triangle, specifically this one. So one thing to note here is what we could do is we could reorder our equation. So I'm gonna do it right here. Let me put this. No. So I'm gonna do, let me remind, yes, okay. Let's do it right here. So, reorder x. I'm going to reorder my x so that x is equal to x3, x2, x1. And once we build our A matrix, you'll see why, and hopefully you can build an intuition as to why I did that. I'm going to keep the variable b to be the same, and I don't have to change the order of my equations, but my A matrix now changes, and with my new definition of x, my A matrix now becomes, so I get the coefficient of x3 from equation 1, which is 4, and I get the coefficient of x2, which is 3, and finally the coefficient of x1, which is 2. Same from the second equation, I get the coefficient of x3, which is 0, then I get the coefficient of x2, which is 7, and then I get the coefficient of x1, which is 6. And then finally, in the last equation, the coefficients of x2 and x3 are 0. So x3 is 0, x2 is 0, and x1 is 9. And now, from my reordering, I can see that I have an upper triangular matrix. If this was hard to follow, you will build an intuition to it. You'll see when you reorder it, till you get it right. Once you do enough examples of situations like these, you're going to build up an intuition on how to order your equations so as to build a system like this. So now that I know that it's an upper triangular matrix, I can use the fact that the determinant is going to be the product of the terms on the diagonal. So the product of the terms on the diagonal means A11 into A22 into A33, which is 4 times 7 times 9. I don't know what that is, but I know that it's not 0. So from this middle thing, I could find out that my system of equations does indeed have a unique solution, which I can find easily if I wanted to, but I don't want to. Now let's move on to an even more complicated case. Now I want you to think in 4 variables. We're gonna build an X matrix. I'm gonna keep the same order, no tricks here. It's x1, x2, x3, x4. I'm gonna keep the same order of equations, see what happens. If it's not an upper triangular matrix and there's potential to convert it into one, we're gonna reorder and see what we can do with them. So A, in this case, becomes get the coefficient of x1, x2, x3, x4 from the first equation, which are respectively 2, 2, 3, 4. From the second equation, x1 is 0, x2 is 5, x3 is 6, and x4 is 7. From equation 3, x1, x2 is 0, x3 is 8, and x4 is 9. From the last equation, x1, x2, x3 are 0, and x4 is 10. The determinant will be really hard to calculate by hand right now, but we're gonna again use the fact that for a triangular matrix, the determinant is simply the product of the terms on its diagonal, which is 2 times 5 times 8 times 10, which I know for a fact is not 0. So again, we are gonna get a unique solution. And we note that our matrix A is upper triangular. Moving on, let's just do one last case. And then we're definitely not gonna build it for today. So x1 is, x is x1, x2, x3, x4. B is 4, 28, 22, 46. Get the A matrix. I'm going to do it quickly and just do 0, 2, x2 is 0, 0, 0, then 8, 3, 0, 0, then 2, 3, 1, 0, then 2, 2, 3, 2. Now the point to be noted is that it is a lower triangular matrix, and what I'm going to do is I'm going to get the determinant of it the same way I got the determinant of the upper triangular matrix, which is just get the diagonal terms. It's 2 times 3 times 1 times 2, which is again not 0. I know it's a unique solution. And I know that my matrix A was lower triangular. From the look of it, all the terms above the main diagonal were indeed 0. Now, forward substitution. This is the same system of equations we had here, right here, that we built. Right? And it's easy to see that if I start substituting from x1 to x1 equals 4 and just trickle down and follow a bottom down approach, it'll be a lot easier for me to solve the rest of the equations. So let's do just that. I'm gonna copy our A matrix right here. I'm gonna get 2, 0, 0, 0, 8, 3, 0, 0, 2, 3, 1, 0, and 2, 2, 3, 2. And the B, which is 4, 28, 22, and 26, 46. So my A and B that we found right here. X is in order. I'm not going to write that down again. What I'm going to do is I'm going to start solving these equations. I'm going to start solving these equations starting from equation 1, finding out the value of x, then substituting in equation 2, finding out the value of x2, and so on and so forth. So from equation 1, I'm going to write down, I get 2x1 is 4. I know that this implies x1 is 2. Then I use the second equation and I write down 8x1 plus 3x2 is equal to 28. From here I get 8 times, I know that x1 is 2, and I get 8 times 2 plus 3 times x2 is 28, which also means that x2 is 28 minus 16 is 12 by 3. So 28 minus 8 times 2 by 3, which is 28 minus 16 by 3 is 4. Now for the next equation, I'm going to write 2x1 plus 3x2 plus x3 is 22. From here I build 2 times x1, which I know is 2, plus 3 times x2, which I know is 4, plus x3 is 22. Just to mark what I'm doing here. And hopefully it doesn't get too confusing. Not gonna do it for x4, just for these two equations. Right here. Okay. Alright, take everything on the right hand side. These are all constants for as far as this equation is concerned. And then x3 becomes 22 minus 2 times 2 minus 3 times 4 divided by 1, which is the coefficient of x3. I wanted to write it down just because I could. Finally, the last equation is 2x1 plus 2x2 plus 3x3 plus 2x4 is 46. I solve it, I get 2 times x1 I know is 2, plus 2 times x2 I know is 4. Oh, did I unsolve it? It's 22 minus it's 22 minus 4 is 6. I think I was going for 2, 4, 6, 8. Okay, so 2 times 2 plus 2 times 4 plus 3 times 6 plus 2 times x4 is 46. From here, I rearrange my terms and I get x4 is 46 minus 2 times 2 minus 2 times 4 minus 3 times 6 by 2. And if everything goes right, that's probably 8. Now, why do we go through all of this? Well, we do all of this because there's a nice structure to this problem that we're going to exploit when we're programming it on a computer. We're going to see that there's a structure to it, there's a pattern to it, and we can use it when we're programming in a computer, because the computer is very good at doing stuff that is repetitive. So, how do we do that? We do that by writing down. We're going to note that pattern right here. So from here I get x1 was 4 by 2. What is 4? 4 is the first term in B. So it's B1 by 2. What is 2? 2 is the first term in A, in the first column and the first row. So I and J is 1 and 1. So it's B1 by A1, 1. And that's how I got my x1. Now for x2, I will note that it is 28. Where is 28 in our solution? 28 is right here. So it's B2 by, it's B2 minus 8 times 2. Now this 8 you're gonna get from the coefficient of x1 in the second equation, which is this 8. This 8 right here. And then this one becomes, this term becomes A21. So row number 2, column number 1 times, what was the value of x1? So it's x1 divided by 3, which is the coefficient of x2 in the second equation. This thing right here, which I note is A22. Amazing. I'm going to do the same thing for x3, and then from there, I hope you can just take it. I'm going to move this thing out of my way a little bit. Yeah. And then for x3, I note that this becomes, x3 is 22, which is B3, minus, for x3, I'm going to look at the third equation because it's x3. So for the third equation, I found 2 at the first position, that is the coefficient of x1 in equation 3. And I know that this term right here below the 8 is known as A31. And it's multiplied by the value of x1, which I found was 2, which I pointed right here, minus the second equation. I see the coefficient 3 belongs to x2. So this term right here in our third row, and the second column, so it's A32 times x2, which we found was 4. And we replaced it, which is bringing it back, divided by x, the coefficient of x3 in the equation, which from my A matrix I found is at the position A33. And that's it. That's how we essentially build our general form, and we know that the general form works because that's what we used. We substituted it to solve our problem. Now for the backward substitution, what I'm going to do is I'm going to solve it using the general form. And you will find that the general form is in our appendix. It goes, use the first equation to get the xn by bn by ann, and so on. So that's what I am gonna do. So I use my last equation. I use 10x4 equals 10. Should we do it the way that we did in class? I want to use the formulas. So this from the general form becomes xn. We're going to need the A matrix. We found it right here. So let me just pick this up real quick. Got this. I did not got this. Okay, I'm just gonna remove this. Okay, I'm just gonna rewrite my A matrix. What is my A? Just assume it's from the previous step. It's 2, 2, 3, 4, 5, 6, 7, 0, 5, 6, 7. 0, 0, 8, 9, 0, 0, 0, 10. And then B was simply 20, 34, 25, 10. And my X was X1, X2, X3, X4. What I want to do is I want to find all of these x's. From our formula, which you find in the appendix, I'm just going to write using the general solution C appendix. Amazing. So let's get to it then. So then my x4 is b4 by a4, 4. What is b4? b4 is 10, and a4, 4 is also 10. This term right here. And then I get x4 is equal to 1. I use it in x3. I know from my formula here where n is equal to 4. So I get x4 is b4 by a4, 4. I know x3 is b. I don't know why this is happening to me today. I know that, yep, x3 is b3 minus a3 4 times x4 by a33. Just substituting n is equal to 4. Let me put that as a note. So put n is equal to 4 for problem, what we called, for the forward substitution problem, I call it. Backwards, sorry. And this should be used as a hint, people that are just looking at the solutions. Then I get x2 finally. We've already written those down for you. It's that thing. So, I'm still gonna write it because I need to copy it. So x2 is b2 minus a22 times x3 minus a24 times x4 by a22, and then finally x1 is b1 minus a1. Bad positioning. x1 is b1 minus a12 x2 minus a14 a12 x2 minus a13 x3 minus a14 x4 divided by a11. So in the interest of time, I am gonna copy these things if it will let me. Not like that. Okay, one more time. One more time. Yes. Okay, I'm gonna take this right here. Okay, come on, we got this. Okay, let's take this thing right up there. Come on. Yes, right up here. And make it really small. Really small. Okay, got it. This is my hint. Right. So I found my closed form solution. I'm just going to use these. I get x3 is b3. b3 is 25. b3 is 25 minus a34. a34 is 9 times x4 we just found is 1 divided by a33 is 8. 25 minus 9 by 8, this is equal to 2. Now I get x2 is b2 is 34 minus a22, which is 5, times x2, which I found, times x3. It should be 8 to 2, it should be 8 to 3. Yeah, it should be 8 to 3. Okay, so 8 to 3, which is 6 actually. minus 6 times x3, which is 2, minus a24, which is 7, times x4, which is 1, by a22, which is 5. This becomes 34 minus 12 is 12? No. 34 minus 12 is 22. Minus 7 is 15. By 5 is 3. Great. And then x1, I'm going to use the formula again. b1 is 20. a12 is 2 times x2 is 3, minus a13 is 3 times x3 is 2, minus a14 is 4 times x4 is 1, and a11 is the first term right there, it's 2. I'm not gonna solve. Okay, let's just solve it. So it's 16, 20, so it's 2. So my vector x, my solution, x is 1, 2, 3, 2. Okay, great. Now that we've built this up, hopefully when we're solving it in Julia, I can go over this a lot faster. If there's issues about it, feel free to reach out in office hours. I'm gonna move on to Julia. The solutions that we've done here, right here in class, will be posted. Escape. Okay, wouldn't let me. Alright, for a second there. Alright, so now we move on to the Julia part of this recitation. I'm gonna go over this notebook with you guys. It's not gonna be a lot of writing, so I'm just gonna put this up. Great. Alright, so Julia, so in our homework assignment this time we explained vectors and matrices in Julia, and we thought it would be helpful to go over it in recitations in case anyone was having issues with syntax or just homework problems in general. We're gonna take this as a motivation to learn how to use arrays in Julia. You can really do nothing without arrays in Julia. Well, not nothing, but nothing of great value. So, what is an array? Now, array is a general concept used in programming. It's not something that is only used in Julia. An array is just a collection of objects. What are objects? Objects are data stored in different variables for the purpose of this discussion, basically, but not really. So array is a collection of objects or variables stored or data stored sequentially in our memory that is arranged as a grid. So different elements and stored in the memory, think of it as like a memory stack is what we call it, and then the different elements are arranged in like a sequence. So when we're using vectors and matrices like we do in math, and then we translate it into Julia, we have to use arrays instead. In most programming languages though, when you're using arrays, it's usually like a collection of data of the same type, which is also the case with Julia, but we'll see later how we can play around with it. Now, from our vectors, in math, we know vectors are one-dimensional matrices. They can either be row vectors or they can just be column vectors. Now, Julia understands these as a list of numbers or characters, which we're going to call, we could call objects, but let's stay away from that notation. So vectors in Julia is essentially what you would expect. They're one-dimensional arrays. How do we get vectors in Julia? You don't have to know this way of initialization, but you should know that you're able to do it. So in Julia, if you want to declare a vector, you can just say vector and then specify the type in the curly brackets like we've done here. So to make a vector of int64, we do that. Now you should understand that Julia doesn't actually have a type called vectors as it does an array. An array is actually a primitive that Julia uses. The vector in itself is just another name that Julia gives to an array of dimension 1, like we see here. Now you can also specify the number of dimensions. So let's say I want an array of 10, I want a vector of 10 elements, and I want to initialize it with a random garbage value. So I'm going to call it undef. It's an undefined value. I can initialize my variable a, which has 10 elements in it, all are garbage. The same way, I can initialize a string which just has the specifier hashtag undef in it with 5 vectors. So we can have vectors of integers, strings, you name it. Now, again, realize that this is not something you've done in your homeworks. This is more of an extra knowledge for you to realize that Julia does indeed have vectors and how it's compatible with the math that we do. But it is sometimes useful to understand what this notation means. Not this per se, but the full array notation, because it will help you understand types later when you're debugging your code and you have like an error that just says error in array 10 and undef and these 20 lines of codes thrown at you. If you recognize this one part of it, you know, okay, so I did something with my array, maybe the type wasn't correct, maybe the dimension isn't correct, maybe it's a bounds error. So you have something to work on. So just get familiar with the syntax if you can. The way that we actually expect you to initialize arrays and the way that I think most people in Julia initialize arrays is directly using the square brackets, putting the elements in there and arranging it like you would do in MATLAB, or yeah, how you would do in MATLAB basically, I think. So the A vector is a collection of 5 elements and I separated it by commas, so it assumes that it's going to be a vector. So it's a 5-element vector, which an array of all of this basically means a vector of int64, which we found is comparable, right? So that is how you would write a 5-element vector in Julia. Another thing to note here is that it's automatically a column vector. Now, by default, vectors in Julia are column vectors. Doesn't really make a difference. There's a way that we can get row vectors. You do want row vectors. But if you're going to use the vector keyword, this is what you're going to get. In the interest of time, I'm going to speed this up. Way to get another way to get vectors in Julia instead of using the commas, you can use the semicolons, and you get the exact same thing. Let me remove that. Yeah. get the exact same thing. Now, it's vector A, I define like this, and B, I define like this. What if you did want row vectors? So what you would do is, from your one-dimensional column vector, which you define like that, you'd remove the commas, and that would tell Julia that I want this to be a row vector. You run it, and you see that the type is different. The array is of dimension 2, which you'll see later, and we'll come back to this, but it's of different types. This 5-element array of int 164, 1 is not the case anymore. Now, what happens when I compare these two vectors? Well, let's see. A equals B, that is, it thinks true. What if I try A equals C? False, because you can see that the dimensions, even though the elements in the two are correct, they're completely equivalent. The vectors in themselves are not equivalent. One is a row vector, one is a column vector, and they're just different types in Julia. Now, going on to matrices. Now, matrices in Julia invariably translate into arrays. So, vectors are arrays too. And it also, like, array can be of different dimensions. We look at two-dimensional arrays and we call them matrices. But Julia understands that we as people that study math are more comfortable with calling two-dimensional arrays matrices, and it has built-in functions that lets us do just that. So I'm going to define a matrix. You should understand. Leave how we built a row matrix, and then put a semicolon, and then you put the terms in the next that you need in the next column. So 1, 2, 3 will form the first row, and 4, 5, 6 will form the second row of our matrix. Now, you should make sure that you're not using the commas, because that's going to throw errors, because it expected the first row is translated into a column, and then you're saying another column. It just doesn't recognize the comma except for when you're trying to build a one-dimensional column vector. So stay away from that. It takes a while to get used to, especially if you're used to MATLAB. The commas are okay in MATLAB, but it's not going to fly in Julia, so make sure you're not doing it. Now, do you remember when we said that an array is just a collection of elements of the same type? But then we can, at the same time, we can do something like this. We can build a matrix A, which has integers, and it also has string. How that works is that Julia has this hierarchical structure of types, and the type any can be of the type string and also of the type Julia. So I just typecast everything in this array to the type any, and now it's an array of objects of any type of variable, like the any keyword. So now let's look at the operations that we can carry out on this matrix A. We can see the size of A, which is 2, 3. It's a 2 cross 3 array. We can see the size of A, 1, which is extract the first dimension of A, which is 2, extracting the second dimension of A, that is 3. The length of A will give you all the elements of A, so that's 2 cross 3. There's 6 elements in A, so length of A is 6. The number of dimensions is 2. It's a 2 by 2 array. It just has rows and columns, nothing else. If it was a 3-dimensional array, it would have not just rows and columns, but think of it as like an X and Y and also a Z. But it's only 2 dimensions, so we don't have to worry about it. So this is what I was talking about, like understanding the definition of an empty array in Julia. You'll find it in a lot of code online. You'll find it useful for when you're debugging, and the warning or like the debug statements are all in like using this terminology. So from here, I want you to understand that you can declare an array, an empty array, using array keyword. In the curly brackets, include the type, which goes here. Then include the number of dimensions. If it's a matrix, you want to include the number of dimensions 2. If it's a vector, the number of dimensions 1. Then you want to say that it's an empty array. This part is actually optional, but you want to say that it's an empty array, and then you say the keyword undefined or undef in Julia, and then you pass the dimensions of that array. So when you run that statement, if you're running an empty array, it will initialize an empty array of the type number, and it will build an empty vector. Vector, we remember, is just array of type, of any type and dimension 1. That is a vector, which is what we do in math as well. It's an array of dimension 1, that's a vector. Then we initialize it with the keyword undef, and we want how many elements in it? Well, I want the vector to be of length 2. So I've initialized an empty array, empty vector of length 2 using this statement. Similarly, you can initialize an empty matrix of dimension 2 cross 2. The dimension goes right here. The size goes right here, the size of the array, and the dimension, it's a 2D array, it's a 2-dimensional array, goes right here. The type is number. Now, an array of 2 dimensions has the type alias matrix. I'm gonna rush through this one because it's not important, but you can initialize it just like we did the vector. I don't know what happened here, but anyhow. You can initialize 3-dimensional arrays, so you can think of it as like points x, y, and z. It has 3 dimensions, and you can run it. There's other ways of building arrays. You can use statements like zeros, which will build an array full of 0 with the dimension that you pass, with the size that you pass as an argument. So it's 2, 2. Ones will build a matrix of all ones with 3, 3. Random will build a matrix of 1, 2, a sampling from a uniform dimension. I need to using linear algebra. Similarly, you can build a matrix from that array A, which was 1, 2, 3, 4, 5, the vector that we built. If you pass it to a diagonal, it will make a matrix such that the diagonal elements of that matrix are the elements of that vector. Next thing is indexing and slicing. So let's say I make an